Hello students, today we are going to learn the other two methods of the concentration of the ore, that is magnetic separation and leaching. We are also going to look into the extraction of the crude metal, which consists of two steps, of which one step will be dealt with in this part, wherein the ore is being converted to metal oxide. Now let's see about magnetic separation. Magnetic separation is suitable for concentrating ferromagnetic ores with a difference in their magnetic property between the ore and the impurity. Let's take two ores, wolframite ore, which can be separated from tin stone, where tin stone acts as a non-magnetic impurity. This can be done by electromagnetic separation. Let us see how electromagnetic separation operates. We take the crushed ore, which is fed into the hopper, which goes on to the electromagnetic separator, which consists of a moving belt which rolls over magnetic roller. The ferromagnetic substances which are present in the crushed ore are being attracted towards the magnetic roller, and they fall into a heap near the magnetic roller side, which can be separated, and the non-magnetic impurities not being attracted by the magnet fall into a separate heap nearby. Now we will look into the leaching process. Leaching of concentrated ore means draining away the ore into the suitable solvent. Leaching method is based on the solubility of the ore in a suitable solvent and the reactions in aqueous solution. Based on the solvent that is being used, leaching can be of different types. So they are classified as cyanide leaching, ammonia leaching, alkali leaching and acid leaching. The general process that goes on in the leaching process will be, first the crushed ore is dissolved in a suitable solvent. The metals which are present in the ore gets dissolved in the solvent or dissolves into the solvent. The metal gets converted into its soluble salt or complex form, and it can be recovered by reduction. The impurities which are present, being insoluble, they get precipitated and it forms a gong. Now let's go into what is cyanide leaching. In cyanide leaching, let's take an example of the crushed gold ore. This crushed gold ore is leached with aerated dilute sodium cyanide solution. Aerated means oxygen is being added into it, and it is an aqueous solution, so water is being included. This converts the gold into a complex, a soluble cyanide complex, and leaves behind the insoluble gangue particle, which is called as aluminium silicate, and it gets down its impurity. If we look into the diagram there, we have the ore of gold, which is being crushed into a powdery form. So the crushed ore is being leached with aerated dilute sodium cyanide solution. When the gold gets converted into the soluble cyanide complex, and the impurities, which are aluminosilicate impurities, they get precipitated as the gong. The reaction that takes place in the cyanide leaching is illustrated here with, which will be taken up for balancing. The recovery of gold from this equation can be done via reduction reaction, and this process is called as cementation, wherein when zinc is being used, gold gets precipitated or recovered. Now let us balance the equation that is involved in the cyanide leaching done during the extraction of gold. Now let's write down the equation. We have gold, which is in the solid form, reacting with the sodium cyanide, which is a suitable solvent in the aqueous form, and oxygen and water are present in it in the gaseous form and water in the liquid form. It gives a complex, a soluble complex, which is AuCN twice minus in the aqueous form formed along with OH minus ions, which is in the aqueous form. Aqueous form is represented as AQ. Now balancing this equation, first let us take the number of oxygen atoms which are present in it. So if it is 4 OH minus, then it means that the complex that is formed is also written as 4 AuCN twice minus. So since there are 4 OH minus present here, there are 4 oxygen atoms on the product side. And 4 hydrogen atoms present on the product side. To balance this, on the reactant side, let us put 2H2O. So hydrogen atoms as well as the oxygen atoms gets balanced on the reactant and the product side. Since 4 is being written in the complex in front of it, so there are 4 atoms of gold. So on the reactant side, we write it as 4Au. On the product side, you have 4 into 2, 8 ions of cyanide. So to balance it, on the reactant side, we write it as 8Cn minus. Now this becomes a balanced equation. The first equation is balanced. Now in the second equation, in the cyanide leaching, you have the same gold complex which is in the aqueous form treated with zinc which is in the solid form. When these react with each other, the zinc takes the place of gold, and gold gets precipitated which is in the native form, and the oxidation state of gold is considered to be 0. Now for balancing this one, you have cyanide 4 on the product side. Cyanide molecules, ions are 4. So here there are only 2 cyanide ions. To balance that, we write it down as the complex in front of the complex 2. So now this changes over the cyanide ions to 4 ions there. Now what about this gold atoms? There are 2 gold atoms, or it is considered here as gold ions. So on the product side, we write it as 2Au, which is being in the oxidation state of gold here is considered to be equal to 0. Let us go into the next type of leaching, the second type of leaching, which is called as ammonia leaching. Here in ammonia leaching, as the word implies, aqueous ammonia, aqueous NH3 is being used under suitable pressure. The crushed ore of nickel, copper and cobalt is being treated with aqueous ammonia under suitable pressure, wherein selective leaching of these metals, nickel, copper and cobalt, takes place, wherein their soluble complexes are being formed, which leaves behind gangue, iron oxide, iron hydroxide and aluminium silicates. Here you find nickel crushed ore reacts with ammonia, which is in the aqueous form, to form the complex of nickel. The copper crushed ore reacts with aqueous ammonia, forming a different complex, and the cobalt crushed ore reacts with aqueous ammonia, forming another soluble cobalt complex. So this is ammonia leaching being done with aqueous ammonia. Let us go into the third type of leaching, which is called as alkali leaching. Now in alkali leaching, we are going to take the concentrated ore and we are going to mix it with an alkali. What is the meaning of an alkali? Alkali is a substance which either it can be sodium carbonate or sodium hydroxide, and aqueous stands for substance which is dissolved in water. So when the ore is mixed with aqueous alkali at a particular temperature and pressure, it forms a soluble complex. So now let's take an example of the aluminium ore, which is bauxite, Al2O3. So bauxite, when it is being treated with aqueous alkali will be sodium hydroxide, which is taken, and water is mixed along with it, H2O, the liquid state, and when it is being treated at 470 Kelvin to 570 Kelvin at 35 atmospheres pressure, it forms a complex which is called as sodium meta-aluminate with the formula NaAlOH 4 times, which is also in the aqueous form. This sodium meta-aluminate, which is soluble, is hot and it is decanted, cooled and it is diluted. This solution is neutralized by passing carbon dioxide gas, wherein it forms hydrated Al2O3, which is a precipitate. This precipitate, Al2O3XH2O, is filtered off and it is heated around 1670 Kelvin, wherein pure alumina can be obtained. So this is a balanced equation in which you have Al2O3 and 2 NaOH plus 3 H2O gives us this particular complex. Now in the next type of leaching, we have the fourth type of leaching, which is called acid leaching. As the word implies, acid leaching, sulfide ore especially is being made to undergo acid leaching. So sulfide ore, which consists of the insoluble sulfide like galena or ZNS, is being treated with hot aqueous sulfuric acid when soluble sulfates are being formed and elemental sulfur is also being got. So the insoluble sulfide gets changed over into soluble sulfates and elemental sulfur is obtained. The equation would be 2ZnS. If you take the ore as ZnS, you have zinc sulfide in the solid state being treated with hot concentrated sulfuric acid, hot aqueous sulfuric acid along with oxygen. When zinc sulfide gets converted into zinc sulfate and elemental sulfur in the solid state is obtained along with water molecules. In this process, the insoluble sulfides are converted into soluble sulfates and elemental sulfur. After the concentration of the ore in the metallurgical process, we come to the next step, which is extraction of the crude metal. Now, the crude metal is a metal which is not in the pure form. Now, what is the oxidation state of the metal in the concentrated ore? We have some examples of the ore like PBS, ZnS, PbCO3, CaCO3, ZnCO3, etc. Now, in all these ores, you find the sulfide and the carbonate ions are oxidation states are negative. Hence, the metal which is involved along with them will have to be in the positive oxidation state. Thus, the metal will exist always in the concentrated ore in the positive oxidation state. Now, what are the steps which are involved in the extraction of the crude metal? So, since the metal exists in the positive oxidation state, first we are going to convert the ore into the oxide of the metal, and secondly we are going to reduce the metallic oxide to the elemental metal. From the principles of thermodynamics, the reduction of oxide is easier when compared to the reduction of other compounds of the metal. So for easier extraction process, the ore is first converted to the oxide of the metal of interest. Now the conversion of the ore into its oxide can be done through two steps, roasting and calcination. You will be given a question as differentiate between roasting and calcination. As the word roasting implies, you would have seen in your daily lives, there is a roasting of groundnuts wherein they roast it in open air, that is with excess of oxygen. So in roasting, the concentrated ore is treated with excess of oxygen in a suitable furnace where the temperature is below the melting point of the metal and the metallic oxide is being formed. This roasting process is being applied to all sulfide ores, wherein the sulfide ores are being converted to their metallic oxides. And in this process, you can remove the impurities like arsenic, sulfur and phosphorus by converting them into their volatile oxides. Lead sulfide, the sulfide ore, On heating with excess of oxygen gets converted into lead oxide, the metallic oxide, and sulfur gets oxidized to sulfur dioxide. The impurities such as arsenic, sulfur and phosphorus can be removed off as volatile oxides. So next we go on to the process which is called as calcination, wherein we are going to convert the ore into their oxides by the process of calcination. Calcination, as the word starts with C, is usually done for carbonate ores. And you will have to remember that during this calcination process, the concentrated ore is treated with limited supply of air or in the absence of air, and the concentrated ore gets changed over into metallic oxide. For example, you have lead carbonate, calcium carbonate, zinc carbonate. On heating them, they get decomposed. What's the meaning of decomposed? It breaks down into their respective oxides and carbon dioxide is liberated. And the last equation you have MgCO3 on heating gets decomposed to magnesium oxide and carbon dioxide. If you look into your books, to page number 8, you have an evaluate question which goes like this. Magnesite, that is magnesium carbonate, is calcined to obtain magnesia, which is used to make refractory bricks. So magnesium, which is MgO, is used to make refractory bricks. You are asked to write down the decomposition reaction. So just like the previous 3 reactions, you write down the equation for this as MgCO3 on heating gets decomposed to MgO and carbon dioxide. During this process of calcination, the water of crystallization present in the hydrated oxide, it escapes as moisture, and any organic matter, if present, also gets expelled, leaving behind a porous ore. This is a flow chart for the extraction of the crude metal for metals of various reactivities. We have metals of high reactivity, medium reactivity, and least reactivity. So those metals of high reactivity, for example, the alkali metals, can be extracted by the process of electrolysis of the molten ore, wherein the pure metal can be obtained. Those metals with medium reactivity, if they are in the form of a carbonate ore, they undergo the process of calcination under the extraction of the crude metal. And if they are of the sulfide ore, they undergo the process of roasting in the extraction of the crude metal. In both these cases, you find the metal being converted into its metallic oxide, and then the reduction of the metallic oxide to its metal takes place, and after which purification of the metal is done. The metals of least reactivity like gold, silver, if they are present in their sulfide form, they undergo the process called as a roasting, from which the metal is being obtained, which can be further purified. The second step in the extraction of crude metal is reduction of metal oxide. In the reduction of metal oxide, a suitable reducing agent can be used for a particular metal, and it can be classified into different types, which may be smelting, reduction by carbon, reduction by hydrogen, reduction by the metal, or auto reduction. The suitable reducing agents may be carbon or carbon monoxide, hydrogen, aluminium, sodium, etc. They can be used to reduce the metal oxide. The choice of the reducing agent, it depends on the nature of the metal, which will be dealt in Elingham's diagram in the further videos. Thank you.